สียงมันดีเลย์ช้าคือมันต้องพูด
อันนี้มันไม่ค่อยดีเลย์กันเท่าไหร่
ไอ้ตัวเนี้ยคือเมื่อกี้เขาพูดตรงนี้เสียงขึ้นตรงนี้ไม่ขึ้นเลยเมื่อกี้เช็คต้องมาพูดแล้วคนยังไม่มาเลยคือส่งไปสวิตด้วยนะครับนึงขอเข้าน้ำรถคน
2 อันนี้ไหม
ลองกล้องเนี่ยคือสลับกันนะแล้วก็มันสามารถเฟดได้ด้วยไงเฟดพรีวิวกดพรีวิวข้างบนอ่ะ
เอาทำเป็น PNP อ่ะ
จะเลื่อนขึ้นทำไมล่ะครับมันออกอาการแล้วนะครับ
เอาละก็มันเป็น PNP อันเล็กไง
ก็ต้องได้ประมาณนั้นนะ
Sorry.
ครับ
Question. Do I need to use the microphone?
Microphone.
Do I need to use? Or
เขาต้องการถามเรื่องไมโครโฟนนะไมโครโฟนไวเลสอะ
ไวเลสไมโครโฟน
ไวเลส
Okay, I will. Get that.
บอกเขามีอันเดียว2 อันเสียงไม่เข้า
คือว่าไมโครโฟนมีใบสายครับมันฝากดูนะ
เฮ้ยรอก่อนดิ
เข้าห้องน้ำ
เอาแล้วมองแบบที่ห้องน้ำแล้วน่าจะมีงานอะไรของเขาอ่ะ
คือพี่พอมาเลี้ยวไปทับจันที่ลงป้ายแรกแล้วเดินย้อนขึ้นไปฝั่งไม่มีรถเมล์กันตรงนั้นรถเมล์มันต้องวิ่งมาอ้อมบนรถติดโคตรเลยอ่ะเมื่อเช้าติดแล้วไม่ติดใช่
สั่งของพ่อไม้แม่ไม้แม่ไก่อันนี้เก่งอยู่สมาคมพ่อไม้แม่ไม้แล้ว
เปล่าลองดูดูสาว
แม่ไม้อะ
ดูแอดเข้าไปดูแอดเฉยแล้วมึงแต่ละคนที่จะบางคนไม่สวยบางคนหน้าตาไม่งั้น
มันแค่ว่าชัดบางคนมี
ได้เนี่ยเคลียร์เก็บเป็นทึบไปเลย
คืออันนี้น่าจะเสร็จประมาณ
ผ่านแล้วมั้ง
บ่ายสอง
เออ
คือบ่ายสองเนี่ยก็เอาชุดนี้กลับไปก่อนชุดนึงก็เหลือไอ้ตามพวกต่างเราใช้ต้องเยอะก
เขา
ว่า
บอกว่ามีห้องระหว่างห้องไหนห้องนี้ป่ะ
ห้องใหญ่ใช่ไหม
ห้องใหญ่ห้องมี
ห้องเดียวเปล่าผมมองมาให้กูอันหนึ่งที่ได้ตามกูได้แค่แบบอยู่กูเดินเล่นมาแล้วก็มันไม่ตามติดต่อกูไม่ได้
เนี่ย
ห้องระหว่างตอน6 โมงเย็น
เอาดูตัวดีให้กูด้วย
กูก็ไม่รู้ไงมันวางอยู่ตรงนี้
เอาอันนั้นมา
เฮ้ยนี่ของเรา
ไม่ฟ้องไปอยู่ห้องไหนอ่ะ
เอาไปก่อน
คือตอนนี้มันจะมีอยู่แค่เหลือ
ตอนนี้มีอยู่ห้องนี้อยู่ห้องเดียวไง
ที่เหลือมันจะเหลือ3 ห้อง
สามห้องนี่คือไม่รู้เหมือนกันว่ามัน
แต่
มันจะมีว่าต้องถ่ายเสร็จกี่โมงเรากี่โมงถ่ายรูป
เลิก4
ก็ไม่รู้ว่าผู้วิจัยเขาจะมากี่คนเนี่ยเขาจะมอบอะไรยังไงด้วย
เลิกประมาณ5 โมงห้องอื่นอีก3 ห้องห้องนี้น่าจะเสร็จก่อนแล้วเก็บกลับก่อนได้
ไม่ตรงนู้นอ่ะอะไรที่เคลียร์ได้เคลียร์ไปเลยช่วงหลังเที่ยงก็ได้หลังบ่ายเสร็จแล้วเสร็จมาเคลียร์เก็บไปเลย
ของพี่หนุ่ยชุดสงสัยไม่ไหวอะพี่หนุ่ย
ชุดคอมอะกับได้
ไม่พวกกูเอารถมาก็ได้คัน
สภาพ
แต่เพราะกูต้องมาคันสุดท้ายเพราะว่ารถตู้ต้องไปก่อน
คือรถตู้อ่ะมันจะได้คือช่วงประมาณบ่าย2 บ่าย 3ที่จะใช้ได้
นั่นแหละก็เก็บของที่นั่นหนักไปหลังสักหลังไม่ได้ก็ต้องเก็บรอคนอื่นเนี่ย
เก็บพวกอุปกรณ์ไปก่อน
ที่เก็บไม่ได้เดี๋ยวก็นี่ยังอยู่เพราะห้องนี้น่าจะสุดท้าย
ห้อง
ห้องนี้ก่อนเลย
ก่อนเลยไปเสร็จแล้ว
ถ้าเสร็จแล้วก็เอาตรงนี้ไปก่อนเลย
ไปก่อนเลย
ห้องนู้นเอาไปก่อนไอ้บอมหมดฝั่งนั้นไปให้หมดเพราะว่าให้มันขนของของเราอยู่นี่
เพราะว่าห้องที่เหลือมันก็มี3 ห้องก็แค่3 คนก็พอ
ไปให้คุณขน
ไอ้จิ๋
ตัว วเอง
ไอ้จิ๋วแม่งบอกอาจารย์จูนชุดแม่งไม่รู้ว่าดีนะดีสุดชิ้นแล้วก็ชุดนี้อะไรจะเกิดแผน
เขาเลยมาคนเหล็กเขาต้องเอามัน
เดี๋ยวนี้
กูเมื่อวานกูบอกว่าท่านทิ้งตู้
คุยอยู่ด้วยคนเดียวเนี่ยเป็นหน้าที่อะไรของเนี่ย
Hello.
กดแล้วนะ
Good morning, ladies and gentlemen. Our keynote speaker in this morning is Professor Nuno Araujo, and he is among one of the youngest professor at the age of 33 in theoretical and computational physics. University of Lisbon, Portugal. He received his PhD in physics at University of Minho, Portugal, 2009. Then he became a postdoctoral fellow at Institute for Building Materials, Italy, Switzerland. He has published over 50 papers in high-impact journals. He was invited as a speaker 24 times around the world. His research interests focus on the use of statistical physics concepts and methods to understand nature. He has been mainly engaged in the development of stochastic model to study emerging property in different systems such as colloid and nanoparticles, absorption on regular and pattern substance, and atomistic deposition on crystallized substance. More recently, he has been also working with opinion dynamics to study electoral processes and thinking about the fascinating subject of explosive percolation, compact network structure, and dynamics, navigation of optimal path crack, Apollonian packing and network, thin film epitaxial growth, absorption of segments on a line, mid-air collision enhanced saltation, optical synchronizability of bearing, fracturing, highly disordered materials, how to suppress undecided synchronization, overspill or balancing. So tired. Yeah, but I still have more. Can I press it? Okay. And along coastline, some publications were selected as cover of physical review letters and editors' suggestion. His work has been highlighted in Physics Focus, Physics Synopsis, Physics World, Physox, Speaker Online, CNN, were Industrial Reporter, and many more. Please welcome Professor Nuno.
Thank you. So good morning to everyone, and thank you for the kind introduction. Thank you very much for inviting me to be here today. It's a big pleasure to be back in Bangkok and to have the opportunity to show some of our recent results. So what I decided to talk today is how to use the concepts and methods from complex network theory or graph theory in order to study network-like infrastructures. And I will focus in two different examples that are two recent works that we have been doing over the last 3 to 4 years. So the first one is related with a network of water reservoirs in the northeast of Brazil, and the second one with the World Airline Network. So before starting, let me just show you my collaborators. So the work that I will be showing to you was done in my previous position at ETH of Zurich. I was working in the group of Professor Hans Hermann that is here in the room and is one of the speakers today. And we did this in collaboration with two PhD students, Trivik Verma that comes from India and Vitor Lozada that came from Brazil. And for the first part of the work about the water reservoirs in the northeast of Brazil, we did this work in collaboration with two hydrological engineers from the state of Ceará. And so what we are interested to understand is not just the robustness of a single element of the infrastructure, like for example a water reservoir or an airport, but rather to understand how the topology of interactions, how the way the reservoirs are connected or the airports are connected affects the global dynamics. And graph theory provides us the tools to represent this topology of interactions in terms of a graph. And in a graph we have nodes that are the agents, and we have links that are the interaction between the agents. And so in the first case, the the nodes are the reservoirs, and the links are the connection between the reservoirs. So if two reservoirs are connected, this means that water that comes out from one reservoir upstream will end up in another
การส่ง
reservoir
ที่เรา
downstream.
อ่านนะ
In the same line of thought, in the case of the airports, two airports are connected,
หัวกินอ่ะ
means that there is a direct connection or a direct flight from one airport to the other.
สองเลยนะ
And so another concept that is important is the concept
รู้
of
ได้ไง
degree.
ว่าขั้นตอน
So degree of a node is the number of links of a node. So for example, this node here has degree 3 means that there's 3 different links. So in the same way, this one has degree 2 and this one has degree 1. And this is a concept that I will probably use many times during my talk. So let me go through the examples. So the first example is a network of water reservoirs in the northeast of Brazil. So here in this picture, you see in this panel Brazil, and in the northeast of Brazil there is a state, the state of Ceará, and in the south of this state there is a river that is the Jaguaribe River. What is interesting about the catchment basin of the Jaguaribe River and the entire region is that the weather conditions are quite extreme. So we have short periods of a couple of months where we have intermittent rain, followed by several months in a row where we have no rainfall. So where we have a lot of dry weather. So what is important is to have a good network of reservoirs that are able to collect water during the rainy season and to cope with the demand of water during the dry season. Okay? But what is interesting, so this is the region, and each node that you see here is a different reservoir. And what is interesting is that the 4,000 reservoirs that we can find in this region were constructed not based on a global planning, but rather on, in most of the cases, by the farmers to cope with their needs for farming during the dry season. And so it's interesting to understand how this system self-organizes and leads to what we have now today in terms of network, and how the way they are connected affects the dynamics of water. Okay? Just to give you some figures about the region, we are talking about a catchment area that is of the order of 25,000 square kilometers. And there we found 4,000 different reservoirs, but these reservoirs are quite broad in terms of size. We can find very small reservoirs, the ones that I said that were built by the farmers, that have capacities of the order of 2,500 cubic meters, while we also find very large ones with a capacity of the order of 2 billion cubic meters. Another interesting thing is the relation between the amount of rainfall over the year and the amount of evaporation. So in terms of rainfall, we have annual rainfall of around 800 millimeters, but the evaporation is of the order of 2,000 millimeters. So as you can see, there is an important balance not only between the amount of water that falls directly in the reservoir, but we also need to take into consideration, because it plays an important role, the amount of water that falls on the mountains and then runs off towards the reservoirs. Okay? And we are talking about a set of reservoirs that provide water for 500,000 people in the region. So, as I said, the weather conditions are quite extreme. For example, during the dry season, this is a typical picture. So what we have is a completely dry environment. While if we go to the rainy season, we have the rivers completely full and also the reservoirs. And so, if the plan of the size of the reservoirs is not properly done, what we have is that during the rainy season, after some time, most of the reservoirs are overspilling. And so what we can see is situations where, due to the overspilling, even some destruction of the infrastructure is concerned. So just to give you a more visual picture of the weather conditions, what I show here is the set of the 4,000 reservoirs, where each node is a reservoir, and the color is related with the amount of water. So the brown color corresponds to a completely dry reservoir, while a blue color will mean that the reservoir is completely full. And so what I will show it to you is a video over the year of 1991 with real data. And what you see here in this ruler is the amount of water that fall during the can see is that when we start January of 1991, most of the reservoirs are completely empty. As time starts to go higher, then in the beginning there is a lot of intermittent rain. We have days that rain a lot, followed by days that there is no rain, and the reservoirs start to fill up. When we arrive more or less to April, almost all reservoirs are completely full, but then starting in May, the rain stops, and when we arrive to October, you will see that once again the reservoirs are completely empty. So as you can see, though we have a lot of reservoirs, they are not able to maintain the local needs, because when we arrive to October, all the reservoirs are practically empty. Okay, so to understand how this evolves, we decided to look more carefully into the dynamics of water in these reservoirs. So the first thing that we need to do is to find where the reservoirs are. So to do that, and this is an important message that I want to pass during this talk, is that all the real data that we used here is available on the internet. And so there is no need to make any special contact in order to get this data. It's possible to access online. And so what we did for localizing the reservoirs was to collect satellite pictures from the region. And we decided to do for years that there was a lot of rainfall. Why we did that? Because by processing the satellite pictures from after a long period of rain, we can easily identify where the reservoirs are because they are full. But more than that, we not only can localize them in space, as we can also estimate what is the maximum area of the reservoir because it's full. And by using local knowledge about the properties of the landscape, we can now relate this area with the volume of the reservoir, and therefore with its capacity. Okay? So by looking to the satellite pictures, we can first localize the reservoirs, and second, we can estimate what is the capacity of each reservoir. Another thing that we did was to look into the topography of the system, of the region, to the landscape, and to trace the watershed lines corresponding to each reservoir. So we can get the water catchment basins for each reservoir. With that, we will be able to know what is the area where, if water falls there during the rainy season, what is the area that is collecting water to a certain reservoir. And more than that, we can know how the different catchment areas are connected. So we know if water comes out of a certain reservoir, what is the next reservoir downstream that will receive the water from this reservoir. Okay? And so what you see here is the positions that we identify for the different reservoirs, where the color is related to the distance to what we consider the most important reservoir, that is the Oros reservoir, because it's here where the river goes out of the region. Okay? And so different colors means different distances, but not physical distance, but distance in terms of intermediate reservoirs that I pass when I go through the river until I arrive to the last reservoir. So for example, the ones in brown, they are at the distance 1, means that they are directly connected with the Oros reservoir. The ones in dark blue, they have 2 connections, means that we need to go first to a brown one and then to another one. Why this is important when we are looking to the dynamics of water? Because this tells me how many reservoirs will overspill until a certain amount of water goes from one reservoir upstream to a reservoir downstream. Okay? And so what we can see immediately from this picture is that the physical distance is not the only relevant thing in the system. Because you can see that you have certain reservoirs far apart from the Oros reservoir, but they are directly connected with the Oros reservoir. So this means that if there is an overspill of a reservoir here, will directly affect the Oros reservoir. While we have others that are very close, and if they overspill, there is an intermediate reservoir that can somehow work as a buffer and will avoid to affect directly the Oros reservoir. Okay? So here is just a different representation of the network, where you see in the center the Oros reservoir, and different layers corresponds to different distances in terms of reservoirs to the Oros reservoir. Okay? It's just a different way of representing. But one thing that comes out from this picture is that we have a quite heterogeneous distribution of connections. For example, you see the Oros reservoir that have several reservoirs feeding with water this reservoir, but you have others upstream that they have very few connections, meaning that they have very few reservoirs that are sending water to this reservoir. Okay? And in fact, if you make a plot of the distribution of the number of connections, or degree, as I said at the beginning, what you see here is a log-log plot. Here is the frequency, and here is the degree. What you see is a kind of power law distribution. But what is important is that though we find several reservoirs with very few connections, we can also find some reservoirs that have more than 400 connections. So it means that there is a reservoir that receives water from more than 400 different reservoirs. What is quite impressive. And if we look now also to the area of the reservoir, we see the picture that I said to you before. So we have several small, very small reservoirs, but we also have some reservoirs that are with very high capacity. But since we are interested in the dynamic of the dynamics of the water, what we decided to do also was to look to climate data. So once again in the internet, we were able to collect time series for the rain and evaporation in several different points in the region for a period of, for the time frame of 20 years. So using this data, we managed to come up with a hydrological model where we account for the balance between the amount of water that enters in the reservoir and the amount of water that comes out from the reservoir. And so we have a reservoir, and in a daily basin, we know how much rainfall directly in the reservoir, how much rainfall inside the catchment area and runoff towards the reservoir, that is only a percentage of what falls outside of the reservoir, and we know how much was the evaporation. So by balance the two, we can control in a daily basin what is the amount of water in the reservoir. If the amount of water goes above the capacity of the reservoir, then what we have is an overspill. And so part of this water that comes out from the reservoir will go to the reservoir downstream. And so we are interested in the dynamics of the water, and we are interested to identify these overspilling events. So what we decided to do was to calculate the size of the avalanche. So what is an avalanche? If a reservoir overspills, you will send water to another one downstream, and because now this water was added to the volume of water that was already in this reservoir, might be that it causes another overspill. And so an avalanche is a sequence of different reservoirs that are being overspilled and were triggered by the first event. Okay? And what we impressively found when we plot the frequency of events, again as a function of the size of the avalanche, of the number of reservoirs that overspill within one day, what we find is again a power law behavior. And once again, this means that we have very small events that only affect a small number of reservoirs. But we also find very large events. In particular, we found over the years many or some events that were involving more than 1,000 reservoirs. Okay? It's more of the order of 2,000 reservoirs. So this means that in certain days we had half of the total number of reservoirs in the system overspilled. And when you look in terms of the affected area, you see that these large events, they affected something like 10,000 square kilometers of the entire area. And the catchment area is 25,000 kilometers. So it's like more or less half of the entire area that is involved in the overspilling event. So, as I said, the level of water that we were analyzing is based on our hydrological model. And so in order to check if we are having good quantitative predictions, we decided to take the Oros reservoir, and for this reservoir there is available data about the amount of water in the reservoir over the years, and we compared this amount of water with the one predicted by our hydrological model. And so this is what I'm plotting here. So on the vertical axis what you have is the water volume. On the horizontal axis what you have is the year. And the black line is the real data, while the green line is the numerical data. And what you can see is that in most of the cases we find not And so, as I said to you, we need to account not only to the water that falls directly on the reservoir, but also the one that falls in the entire catchment basin. And for that, we need to estimate what is the runoff coefficient, what is the amount, what is the percentage of water that falls in the mountain that will run off towards the reservoir. And after a long period of rain, what happens is that the properties of the soil are changed, and in fact you have more runoff than what you would predict based on the normal properties of the region. And that's why after long periods of rain, you have a peak in the real data that is larger than what we observe with our numerical model. So this means that our predictions are even underestimating what might happen in the worst case scenario. And so for the first part, this is what I wanted to show to you. The first thing is that we can collect data on the web and use this data to analyze the properties of a certain region, in this case, this network of water reservoirs. And that by doing that, the next step that we can do is try now different configurations and sizes of the reservoirs and test how the dynamics will change if now we construct a new reservoir, or instead if we decide to make different connections between the reservoirs. And this is in fact what we will try to do in this second publication. I have no time to show to you the results, but you can check it out. Very good. So in the second example, what I would like to talk about is the World Airline Network. And just to give you an idea, in the year of 2011, according to the available data, around 3 billion people used the air transportation in order to meet their personal and professional needs. And this is rarely the case that we hear about a large airspace shutdown, but in fact, this can occur. And one example was in 2010 in Europe, when there was the eruption of a volcano in Iceland. And because of that, about 100,000 flights were cancelled over 8 days. Due to this cancelling of flights, about 10 million people were unable to travel to their destination. And so just to give you a more visual picture of what happened, this is a video of the region during these 8 days. So in the beginning, only very few airports were working. So you can see like a blackout in Europe in terms of flights. But as the time started to go by, you will see that more and more airports started to open up again, and you'll see that the air traffic increases. And this is when it went back to normality. In fact, England is not yet working. Okay, so what is important is to understand what is the structure of the World Airline Network, how robust is this structure, and in the end, our ultimate goal is to be able to come up with some design rules to know what can we change in the actual system to improve the robustness of the system. And what is important is that we do only mild changes, because we don't want to make big changes in the system. And so what we did once again was to go to the internet to collect data about all the flights and the airports. Every time there is a flight or a connection between two airports, this plane gets an IATA code. This is more or less the code that we see in the airport, in the screens of the airport. And so different connections will have different IATA codes. But for example, if you have a regular connection every morning and night between two airports, very likely it has the same code. So the number of really different IATA codes means how many redundant or how many possible connections exist between two airports. Okay. By looking to the data, we identify the airports that are shown here in this map, and we are talking about more than 3,000 airports, and the number of IATA codes were more than 60,000. Okay? This means that we have around 18,000 connections, because as I explained, there are redundant connections between the airports. And so the first first thing that people do in networks is to look to the community structure. So there are strategies to identify communities based on the way on the weight of the connections between the different airports, for example. This was done already before by other groups, and what they show is that the community structure more or less reproduces the continental distribution of airports, apart from small differences that are typically related with economical agglomerates. But what I will show to you is a different structure that we found by looking into the data. And so, as I told you, we are interested about the robustness of the system. And so typically, when we fly, what we want is that if we want to go, for example, from airport A to B, and if this flight is cancelled, the system will be robust. If there is the possibility to go from A to B by only going through one more airport. So this is what we call a triangle. Means that if there is a triangle, means that there is a set of 3 airports that are mutually connected in this way. And so by looking to the structure of the triangles, we will have an idea of how the system is resilient to failures or to the cancelling of a flight. And so what we do is what we call the triangle decomposition. And so just to give you an example, we have here a toy network. And so the first thing we do is what we call the zero core. Means that every node that is there belongs to, doesn't need to have triangles. But then the first thing that we do is to remove all nodes that have no triangles. So they are not part of triangles. So they are in the extremes of the network. So in this case, what we will remove is the nodes in green, because they are not part of the triangle. You can see that, for example, this node cannot be removed because it's part of the triangle. Okay? When we do that, we get what we call the one core. Means that all nodes that are there have at least one triangle. Well, you can do this process iteratively. Now we can remove the ones that have one core. And when you do that, you notice that just because you remove this one, because it's only part of one triangle, now you have this one here that will have only one triangle, so you also need to remove it. And so when you do that, you get the 2 core. And you can do the process iteratively. And when we did that for the World Airline Network, what we noticed is that in the end we get to a point where we have a cluster. When I mean a cluster is a set of nodes that are connected, that is so strongly connected that by removing one, we will remove the entire set of nodes in the system. And what is interesting is that this core that I represent here in black, this highly connected core, is only 2.5% of the entire set of airports in the system. And though we will think that this core is very important to keep connectivity in the system, what is also surprising is that by removing these hubs, we will only get 8.5% of the system to get, or the airports to get disconnected. So still, when we remove these hubs, 90% of the airports are still accessible, meaning that we can travel from one airport to another one, avoiding going through this core. Okay. Another interesting thing that we saw was related with the periphery. So what we can do is to plot how many airports are still connected as a function of the fraction of removed connections. So we will sequentially remove connections from the network and see how the global connectivity is affected by removing connections. And we follow 3 different strategies. The first one, the black line, we remove the links with the lowest number of passengers. In the yellow curve, what we do is that we first remove the ones with more passengers. And in the blue case, what we have is a random removing, means that we choose one link and we remove, then we choose another one and we remove. So we don't follow any kind of rank. And what is impressive is that when we start removing the ones with the lowest traffic or with the lowest amount of passengers, what we observe is that the system gets disconnected faster than in the other case. So this means that most of the airports are accessible through flights that in principle will be the less economically relevant ones, because they are the ones with the lowest number of passengers. So from these two results and several other analyses that we did, what we conclude is that we have a network structure that is very different from what we typically observe, because we have a handful of economical hubs that are strongly connected and a very vast periphery that is typically weakly connected. And more important than that, if we remove the hubs, most of the network is still connected. And so, as I said, our ultimate goal is to be able to understand the robustness of the system, but also how to improve the robustness of the system. And we have all the necessary data for that, because we know the position of the airports, we know the connection between the airports, we know the number of passengers per airport, we know the number of redundant connections between airports, and we also know the number of passengers in each connection. So what we developed was a strategy to test different small changes in the system and see if this will improve or reduce the robustness of the system. And so how we typically define robustness? What we typically do is that we start with the network and we follow a certain strategy, like I showed you before, of removing nodes or links. And we plot how the fraction of, in this case, airports that are connected changes as a function of the fraction of removed nodes. Okay? And when you do that, you get a curve like this black line here, and so we define robustness as being the area under the curve. In the particular case of the world airline network, we are interested also to affect the minimum number of passengers. So basically we do the same curve, but we weight this curve in terms of the total number of passengers in this cluster of connected airports. Okay? So the idea is that we have a sum over the number of passengers that are still being able to go to their destination. And so when we do that, now we can analyze what is the actual robustness of the system, but we can also start to change the topology of the network and start to see if these changes will either improve or reduce the robustness of the system. But since we are talking about world airline network, if people want to go, for example, from Frankfurt to New York, there is no advantage of changing this connection by a connection between Dubai and Kuala Lumpur. Okay, so what is important is that these changes are somehow local. And so what we decided to come up was with the idea of a cooperation range. That is a distance where it starts to justify to make this connection. Okay? So the idea is very simple. We choose one node or one airport, let's say airport I, and we choose one connection of this airport. So one flight that goes out of this airport. And when we do that, we use a probability of choosing a certain connection among all the connections that is weighted by the number of passengers. So the idea is that the probability that the link that we will change is higher for connections that have less number of passengers, because we want that this change affects the minimum number of people. Okay? And so once we have this connection, now, as I said, only justifies to make these changes within a certain range. So for each airport, we define what we call a cooperation range, V, a certain distance, and we look for other airports within this distance. Okay? And now I look for all airports that I can find within this distance, and I look for all airports that I can find within this distance, and in order not to affect the total capacity of the airports or of the region, what I do is to look for another connection between two airports that are within the same region. If I find two links of this type, now I swap the links. It means that I change one link to the other, and I check how this affects the global robustness of the system. If there is an improve in the total robustness of the system, I accept the change. But if there is no improve, then I go back to the original configuration. so as you can imagine, the amount of improvement that I can get will depend on the distance V that I choose. Okay? And so one thing that we did was to plot the robustness. In fact, this is how much the robustness is improved compared with the actual case, where 0 means that there is no improvement and 1 is the maximum improvement that we can estimate using theoretical arguments, as a function of this cooperation range. And so what we see is that for very small cooperation range, there's no change in the robustness of the system because there is no airport at a certain distance. But as we start to increase this cooperation range, we find an increase of the robustness as a function of the cooperation range. And we find a critical value that is identified with this peak, above which starts to justify to make changes. So there is a critical cooperation range above which it justifies to make changes. And this depends from continent to continent. In fact, if we plot now this critical value, so what is the minimum value that I need to look in order to start to justify? And I plot it for different continents. I will see that we find a linear relation with the ratio between, with the square root of the ratio between the area of the continents and the number of airports. More or less gives you a length scale of relevance of a certain airport. It's typically related to the typical distance between airports. And so we also did the same for other networks like the railway transportation and power grid, and we find the same kind of behavior. Another interesting thing is that we find a power law increase of the robustness with the distance to this critical value. So for those of you that are familiarized with phase transitions, this is a framework similar to the one of the phase transition. So what we observe is that there is an exponent that characterizes how the robustness increases with the distance to this critical cooperation range. And the only continent is different is Australia, because in Australia we also consider as part of the group of Australia the islands from the Pacific, and because of that they have a different topology, so they have a kind of different behavior. But to understand better what are the important features in the network that are leading to this kind of result, what we decided to do was to come up with a very simple. So what we do is we start with our imaginary world, and we randomly distribute the airports in the system, and we use a normal or a Gaussian distribution of the grid or number of connections. So completely different from what we find in the real system. The only ingredient from the real system that we keep is that 2 airports are connected with a probability that goes with the inverse of the distance to a certain power alpha, so with a certain exponent alpha. Okay? And so now we analyze the properties of the robustness, how the robustness changes with this cooperation range for different values of alpha. And what we find is that if we tune this value of alpha to be equal to 2 or around 2, we get the same exponent for the way the robustness grows with the cooperation range that we found for the real system. And why we got so excited about this alpha equal to 2 is that when we go to the real system and we look what is the value of the alpha in the real system, we find a value that is also close to 2. So the most important ingredient is not how the airports are distributed in space, not also what is the number of connections per airport, but rather what is the rule that leads 2 airports to be connected. And by including just this simple ingredient, we managed to recover again the same quantitative behavior that we find for the real system. So this was my message today. So the idea is that by using these methods of complex networks, you can first understand what is the topology of the system and how the topology affects the dynamics on the network. But also you can start to think about strategies to improve the existing systems or come up with design rules to be able to design a system from scratch that is robust. So thank you very much for your time, and now I will be available for questions.
So
this is the reason why we find several, or we see several airports. For example, okay, let me go back to the map, sorry. So we say several airports, for example, in Alaska. Most of these airports, they only have one flight per day. They are typically associated with oil companies, and these planes only go there to deliver material. But we decided to consider them also in our study, because in principle, you should not be biased, and in principle, any place in the world should be accessible. That's why. Exactly. This is true. But I don't think that they will provide us with the data about the manufacturing.
I think that your method can be applied to the internet as well. Do you have any results about analyzing the robustness of the internet?
Yes. In fact, the original work about robustness cited here, they also consider what happens in the internet and what are the minimum amount of changes that you need to do in the connection between routers in order to perform. This work was done by Professor with one of his PhD students.
I'm not good at in this field, but I just would like to know whether your hydrological models can be applied to flood situation in Thailand, because we have different situations like climate change and also a lot of things like soil, a lot of water, raining season, all the things are different, and your model can be applied for this case, or you have to think about the other area, not just only in Brazil. Yeah, that is the first question. And the second question, I'm not good at, again, I'm not good at it. About the flight, as I know, when I want to fly from like one place from Thailand to USA or to Japan, usually if it doesn't have any connect, like a directly flight, we just have to connect from one place to one, like Narita, and Narita to somewhere else. Usually on computer, they're gonna set the flight for us. That one is follow what kind of model, or they look at the situation, the real situation, or the kind of previous thing that they have said it before, or what did they do, I don't know. And you choose your model to look at that point, or you're gonna help that one to make this your model to apply that point. Which way would be helpful in your idea?
So let me start with your second question. In principle, if your travel agency is not biased, what they do is to choose the optimal path. What is the optimal path? Is typically the one that minimizes something. That could be the time of travel or the cost. That's why when you go to your with Expedia, for example, you typically choose if you want to rank the choices based on the time or on the price. Okay? And so this is included
about phase. Yeah, about phase transition. So you said something about phase transition. I'm not sure. So which data that you have phase transition? Yeah. Mm-hmm.
We can describe the process of increasing robustness with the distance, with the distance to the critical vision range, with the same tools that we use to analyze the phase transition. I'm not saying that there is a phase transition. What I'm saying is that we have a behavior that is we can describe using the same framework, and interestingly we find, as we also find in phase transition, that we find the same exponent for different continents, and we can obtain these exponents when we do the same analysis in a model network where we include this probability of linking that is proportional to the distance to the bar. Okay? It's not that we have phase transition.
Yeah, about your models about the airport network that you have done, this one, will it be available or using in the future soon, or is gonna have to like fix some equation, some all these things again and again, or it have be applied right now?
They can be applied right now. Data is available online. The paper is published, so all the methodology is clearly explained, I hope. And so the paper is from last month, so I don't know.
So you're gonna let anyone else to use it first,
Yeah,
or?
next time you can write to me and I will help.
Oh, really? Okay, thank you.
I'm thinking about the for the water reservoir network. Right now, I'm thinking about the ASEAN power generation. Because right now we have a lot of water resources, right? And but that one are for power generation. So how do you think about your model? Could it be implemented for this kind of purpose?
This is in fact a very important application because when you use hydrological reservoirs for power, what happens is that if you ever overspill, you need to open the doors. So you have no way of producing energy when they are overspilling. So it's really important in that case also to keep the level of the water at the optimal value in order to be able to produce electricity. Because when they are completely full, you cannot produce. You just need to let the water flow. Okay? So it's another example of where it's relevant to know how to construct a system that is able to keep always an optimal value of the amount of water. And it's not just that you increase, this is one thing that I forgot to say, but it's not that you just increase the reservoirs to have a lot of capacity, because you also want to renew the water inside the reservoir. So in fact, over the year, I think it's 3 times the level of water that needs to be renewed. Otherwise, you cannot control the quality of the water. So there are several cases where it's important to have a balance between the amount of water and the amount of renewing of the water. Thank you.
Some further questions? Okay, when you find from particle to here, so you use your model to run.
I did not take into consideration Ukraine, so now we need to be more careful. I need to recalculate for the way back.
So yeah, thank you very much for your lecture. So that so we will have some gift for you from the Vice President.
is 15 minutes.
นี่นะก็พักเบรก15 นาที เข้าไปอีกอ่ะซูมคนที่นั่งวิทยากรเป็นวิทยากรแบบนั่งอยู่เนี่ยแล้วก็หกอยู่เทปอ่ะ5 6เนี่ยไม่ต้องกดเอาหนังสือไปด้วยสักพักอ่ะ
มาเป็นกองโจรนะ
ตาเขาไม่ยอมใช้ไม้อะ
ไม่ใช่เอาใช้
พี่เก่งบอกไม่ใช้เสียงฟุกบอกแทบไม่ได้ยิน
ใช้เอาแล้วตอนเนี้ย
ตอนนี้ไม่ได้ยินเลยเขาไม่พูด
เขาฟังดิไม่ได้ยิน
กินตีนใช้งานได้
Have the last keynote speaker from in morning, and may I introduce Professor Dr. Tung is come from is Kasetsart University. Oh no, sorry, is Chiang Mai University. Is welcome Professor Talk.
Okay, thank you very much. Good morning, ladies and gentlemen. May I introduce myself? I come from Chiang Mai University, from Department of Mechanical Engineering. Actually, Chiang Mai University would like to be a green university, and the waste zero management concept is also one main topic of the university. And for today, we'll give you and share you about our experience about the zero waste management on the biofuels production from biomass. Okay, when we are talking about the biofuels, right, mostly we think about the bio oil, right, bio oil, and mostly the bio oil mostly come from palm oil and jatropha, but in Chiang Mai we are interested in another type of the vegetable oil, that is Tung plant or Tung oil plant. In Thai we call Mayao Hin, and in Laos it's called Macau. And there are big plantations in Laos and southern China. Why Tung oil is very interesting because the yield of Tung oil is quite high. It's in between jatropha and palm oil, and this is non-food oil. Okay, that's That's why this one is very interesting. There is a data that for one ride is the area of around 1600 square meter is one ride, and the yield of the oil is around 300 to 400 liter per ride per year. Compare with the that is very close to the palm oil, okay. And and the quality of the oil is pretty good. Again, it's in between Jatova and palm oil. Okay, this is right because most of the Western people always call Tung oil, right? But the Tung, I think this one comes from Chinese word. Chinese word is Tung. Tung is, I think, we use the extrusion process, okay? And we can get the, after the extraction, we can get the cake, something like that, and also the oil. Okay, this is the normal or practical process. And from now you have a crude VG or Weki oil, right? How to use it? Most of the people thinking about this one, right? Biodiesel, right? Under the transesterification. Okay, but actually there is another simple way. It's simpler. You can blend it directly with the diesel oil. From our experience, we found that you can blend it directly with the composition not over 20%. And you can run it in the low-speed diesel engine without any problems. Just only you have some more emission because of its higher viscosity if you blend it directly. But there is another technique to blend it. You can blend it as emulsion. It means that you can blend water into the oil. And this one you can get a less viscosity, but the emission is less too. Right. Sorry. Okay, this one. Why we are interested about the emulsion? Go back to this one first. Okay. This is the emulsified oil, right? We blend water up to around. We have water 5%, and crude Weki oil is 15%, and we keep diesel 80%. This is the microstructure. You use a microscope, and you can see the something inside the oil. The small droplet that is water. This one is water. You can under emulsify. With the emulsified oil, you can see distribution of water molecules in the oil. And why we are interested in the emulsified oil, right? You can see that you can blend it in terms of water in oil. And in combustion chamber, right, water bursts out first. Then you can get very fine droplet. And this one is very easy to blend it. In our technique, we use ultrasonic wave to blend it, right? Blend it. We have to select the suitable frequency. Then we can get water in oil. Okay, and we found that we run it over 600 hours without any problems. The wear and corrosion is similar to the 100% diesel, but the emissions are less, especially the NOx, because when you burn it, right, in the combustion chamber, H2O under high temperature will dissociate to be hydrogen and oxygen again. And hydrogen will go to combine with the nitrogen. Therefore, the NOx is less. Okay, this I think for this technique it's very easy, right? This is our ultrasonic machine, right? The mixer. Okay. Okay, let's go back to from this one to this one for the transesterification. I think for the people who generate the biodiesel, they know how to get the biodiesel under transesterification. You can blend it
blend the Vecchi oil, crude Vecchi oil with potassium hydroxide and methanol. This is very simple. Okay. On the right-hand side, this is the simple, a normal process for biodiesel production. For that one, you have to heat the oil up to around 60 degrees Celsius and keep it for 4 to 6 hours, and you can get the trans ester oil and glycerol, right? Trans ester oil and glycerol. This is biodiesel, and this is glycerol. You spend around 4 to 6 hours. And there are many methods to generate the biodiesel. For example, this one we use a supercritical biodiesel. That one we use very high pressure and temperature. We can do it. But for this one, we found that the efficiency is not so good because you need a very high pressure and temperature. It means that this technique consumes